Okay, well, I decided to do my presentation on mazes and optical illusions. I always found those really interesting, so I wanted to kind of take some of the things we learned in geometry and apply it to that and see what we could learn. One of the things I've found, or I've always been kind of thinking about, is that mazes can only get so hard. As you invent them, you can use, different kind of tricks, but they're not really mathematical. You can use dead ends, you can use increasing complexity, but all those things really just kind of appeal to increasing the size of the maze, and as it gets more and more complex and bigger, that's what makes it harder. But I've been wondering if there's a way to make a maze even harder than that, or to make it difficult by some other means than appealing to just its complexity. And before you get into that, there's two ways to solve a maze which are related to math. One method is called wall following. You might have heard that trick before. It's where you keep a hand on one wall of the maze at all times, and that will eventually get you out, but only of one kind of maze, which is called a simple maze. And what that means is that there's no breaks in the walls. So you have a passage from one side to the other of the maze, which is clear. There's no walls in it. That's the right answer. And to each side of that, there's tons of walls. So if you were to take those walls and get rid of all the angles in them and blow them up, they would just become two circles, which are completely locked together. And so by following the wall, all you're really doing is like passing between those circles in one way or another. And if you take a lot of wrong turns, they'll end up being much bigger. But either way, you will eventually get there. But it won't work for what's called a complex maze. And complex mazes are when they have something called a floating wall, which is not attached to anything. In other words, there's like two ways to get into that passage and two ways to get out of it also. It's just an island. It's a barrier, but you could be going around in circles around that barrier forever, so it won't work. But you can use something else called Trémaux's algorithm. That's named after a French architect. Hopefully I'm pronouncing that right. And the principle behind that is that you don't go anywhere twice. So you mark the entrance of every passage that you go through, and you just never go through the same one twice, and that will eventually get you out. And so that's two ways to solve mazes. But again, those can only get so complicated, and they just get harder by like adding more elements to them. But I was thinking another way that you can do this is along the lines of the spherical and hyperbolic geometry we learned about on the 15th. And I think the way that would work is because getting out of mazes that are in 3 dimensions, or they're kind of laid out on a 2-dimensional plane, kind of relies on our sense of direction or our intuition, or like our sense of space and how, according to like how reality must be oriented. But if you were to make a maze that existed in a spherical geometry or in a hyperbolic geometry, it seems like our intuitions and our sense of the layout and how something must be laid out wouldn't necessarily apply anymore unless you were really good at visualizing those different kinds of geometries. And so I thought of that because I was thinking about the regular mazes and how they exist in a 2-dimensional space, just like Euclidean geometry, and how that seems to fit with our intuitions. But if you made a maze that would exist in these other geometries, it would still be completely functional, and there would still be one answer to it that really works. But it would get very, very confusing, and even though it would all really work, but it would just like completely scramble your brain. I don't think there's a way to create a maze like that, anywhere like physically right now, because I don't think they could exist with gravity being as it is, just pulling you straight down. as it seems, as we're like here on Earth. But I think they could exist inside a computer. And the reason it couldn't work with gravity is because it seems to us gravity is always pulling straight down. And so since we're standing on the Earth, we can only really have one perspective at a time, whereas the two other geometries, only make sense when you're in them and you have your own perspective, but your perspective is looking all over the place. It could be looking straight down or straight up, and that just wouldn't work with gravity, but it would work on a computer, I expect. And in the area of optical illusions, I looked into a little bit a guy named M.C. Escher, who was mentioned in the book along with Gödel, who wrote the incompleteness theorems. And M.C. Escher is famous for creating optical illusions. He drew some very ornate drawings that featured this kind of staircase, which is called the Primrose Staircase. I wasn't able to get some printouts of his drawings, but if you want to go check them out, they're really cool. One other maze I should mention too is this one right here, which is on the floor of Chartres Cathedral in France. This one is not a maze, it's a labyrinth, and it actually only has one path that goes straight to the center. There's no wrong turns in it, which is interesting. But this is also sometimes called the infinite staircase, and basically with this is that it keeps going either, looks like down forever, but the way this works is all because we can only look at it from one perspective as it's in a drawing, and the perspective is morphing the shapes, so they're not the shapes that they would be in reality. Because if you draw a square, for example, from a particular perspective, it could actually look like a diamond, or like something else that doesn't have 90-degree angles. And so that's how he does that. So it works in drawing, but again, it wouldn't work in reality unless you could use those other geometries to make shapes do impossible things that we haven't observed them to do in real life, as we live it now. And there's a few other things to mention, but I better stop it there. And if you want to go look at those drawings by M.C. Escher, they're really cool.